So we're going to talk about gravity today. One of the things I want to say is that I'm going to leave out the last section, which will still be on the PowerPoint and on the script, so because I don't think it's possible to do that justice within the time available. And secondly, I've had to alter this talk twice since I first scripted it around about January because of experimental results, and the second time was this morning. So we'll come up to that about halfway through the talk. So everybody's always said gravity is going to be one of the most difficult problems in physics. Everything else fits in the standard model and gravity doesn't. We're going to have to go back to fundamental thinking if we want to tackle this problem. So we can't just say, let's start from where we are with the standard model, let's go back to our symmetries and fundamental ideas. Back to lecture 3 and 4, so we can make what might be the key decisions. And use the methodology outlined in lecture 2. So we don't want any model-dependent thinking if we can avoid it. We want to go to purely abstract thoughts and symmetries. What I'm going to say here is that at this point we have to make a decision. We have to say, if the symmetry or the abstract model say so, then we go for it. Whatever the consequences, we go for it. That's part of our methodology. And of course, the well-known dilemma is that both quantum mechanics and general relativity cannot be correct, or so people say. We have to either modify or abandon one of them, maybe both. Now, we've had several theories that have tried to do this, made moves in that direction. We've had string theory, membrane theory, quantum loop gravity, and it depends where you want to start from. And it does depend whether you start from quantum mechanics or general relativity. We could abandon both, but it looks more likely that we could start from one and maybe abandon or modify the other. And most people who've done some modification have decided to start from general relativity and try to fit in quantum mechanics into general relativity. And I think probably it's because general relativity seems to be a more tangible thing. It's about something that we can see more directly. Quantum mechanics is more or less presented as though it's a calculating engine. Now, as what I've previously said, quantum mechanics isn't just a calculating engine, it's got profound meaning. And also, quantum mechanics has been very, very rigorously tested to the point of destruction. Against all expectations, it's not been challenged in anything at all. It's never failed a challenge. But people might say general relativity hasn't either, but we will see about that. General relativity has only explained a few things, and these are a long way from its core principles. However, it may be that we can get away without challenging either. Let's see. So can we accommodate general relativity if we privilege quantum mechanics? I'm going to say, I'm not going to go against quantum mechanics, whatever. I'm going to go for it. As far as I can see, that's the way to do physics. So can we retain general relativity if we go for quantum mechanics? And I say, yes, we can. But we've got to understand general relativity slightly differently to the way some people have previously discussed it. And in fact, the way many popular discussions of general relativity discuss it. We've got to do it differently. We've got to remember that when we look at general relativity, all that we have is a set of mathematical equations, the general relativity field equations. We don't have a lot of physics content as well. We have Einstein started with several different physical principles, and in the end he replaces all of those with a set of equations. So that's what we mean by general relativity, those equations. And ultimately, those equations don't explain gravity, nor did Newtonian theory, that didn't explain gravity either. But it doesn't explain gravity. People often say it does, curvature of space, but it's simply shifting the explanation to another point. And I say it's really not so much an explanation of gravity, but a mathematical description of the effects of gravity on space and time as we measure them. Ultimately, quantum mechanics and general relativity come from different viewpoints. General relativity is really an observer-centered theory. people might say quantum mechanics is, but the quantum mechanical equations are really not an observer-centered theory. It's only when you do the measurements that you get the observer coming in. The same applies to Newtonian gravity. Newtonian gravity is fundamentally a God's eye view of the universe. Einstein's general relativity is fundamentally an observer's eye view of the universe. Maybe that's where the problem lies, in the fact that we've got two different viewpoints. And historically, it's often presented as though one is a replacement of the other. So if you have a physical description of gravity as a force, you can replace it by a geometrical description of Riemannian space-time. And the time component's intrinsically part of space, even though it isn't in quantum mechanics. And that, of course, is one of the main dilemmas. Now, if you present general relativity in that way, you have to accept that general relativity doesn't make any sense until you actually look at the mathematical equations and put some physical meaning into them. And you have the curvature, and then you put in the Newtonian potential as the nearest thing that we can observe to that curvature, to that meaning. But you have to, at some point, do that. If you just look at the general relativistic field equations, they are mathematical. You have to put the physical content in as you solve them for particular situations. And you put the physical content on the basis that at the ultimate scale they become, at the limit they become Newtonian. If you just take them on their own, the general relativistic field equations are a mathematical description of space-time curvature. So you've got to go to a solution of the equations and then connect that with a Newtonian limit, which you introduce arbitrarily. Now, why do you do that? Well, we have good reasons for having inverse square law forces. We know that they're part of three-dimensional space. They're part of the structure of three-dimensional space. And this is how we get a Coulomb-type force, as we would call it, in all the interactions. It's the U1 symmetry group. It's the fundamental statement that this force has a coupling constant, and it's based on spherical symmetry. And if we consider this only as an experimental limit, we lose a fundamental symmetry of nature. There's a fundamental symmetry about point sources involved in this. Now, if we think that symmetries are more fundamental than mathematically sophisticated theories, or they're the origin of mathematically sophisticated theories, they're at the more basic level, then we have to make the decision whether this symmetry is really a true one, whether it is broken at the fundamental level. And why should it be approximately true anyway? Now, if we go back to quantum mechanics, we have to ask, why has gravity never been successfully quantized? And we know the answer, that quantum gravity presents us with unrenormalizable infinities. Nobody's found a way of renormalizing them. String theory has created large, maybe membrane theory, they've created large theories in which potentially this problem might be solved, but nobody has actually managed to completely work out a mathematical theory which does it. The reason why we got non-renormalizable infinities is very simple. All the sources have the same sign, and we can't shield them. We can't shield gravity. You can't put something in the way to stop it. And quantum field theory says that if it's a quantum theory of gravity, it must have a boson of some kind, a gauge boson. And because it's intrinsically an attractive force between light particles, it must be a spin 2 boson. That is fundamental in quantum field theory, rather than a spin 1, like you get between electric charges or any other force. So it would have to be a unique type boson. And when you start looking at spin 2 bosons in quantum field theory, you realise that is another reason why you can't renormalize it. Here we've got what must be the worst fit ever recorded in physics. The worst fit between theory and experiment in the whole of physics, in deriving a value for the cosmological constant. This is quite a simple calculation here. What you're doing on this calculation here is mass to the 4th, because effectively it's just mass, and then the rest is over the Compton radius cubed. So it's mass over the Compton radius cubed, so it's the density. So nobody knows how to do quantum gravity, but we know how to do an approximate calculation doing that. So this is just mass over Compton radius cubed, Compton volume if you like. And you get 5.2 times 10 to the 96. Notice I use H cross here. A lot of people just use H, but I think H cross is more correct. But I think they use H because it's not quite as bad a fit then. It's only 3 orders of magnitude better. Now, if we take the experimental evidence from supernova and from the later probes, the WMAP and the Planck, the vacuum density is about 0.7 times 10 to the minus 26, which means that our estimate is roughly 10 to the 123 wrong. Now, that's very interesting that it's that particular value. It's at least 10 to the 120 and probably 10 to the 123 times wrong. It's higher than experimental data. But it's not only the worst ever recorded, it's the worst possible that you could have. Because Seth Lloyd, for example, has proposed on the basis of the holographic principle, we've got 10 to the 123 possible bit flips of data in the observable universe over a Hubble lifetime. So every single event that could conceivably happen over the lifetime of the Hubble universe, and you'd need every one of those events involved to actually get the correct value. You'd need to use every single bit flip you could possibly have to try to get to the correct value. So it's not only a bad fit, it's as wrong as it could conceivably be. And I say it's not even wrong. Now that's very useful information that it's so bad, because surely it's telling us something. If it's that bad, it must be telling us you shouldn't be looking here, you should be looking somewhere else. It's an opportunity, it's not a problem, it's an opportunity. We should be looking in the opposite direction. Now, gravity has to be quantum. But is it what people call quantum gravity? We can't have quantum mechanics, we're saying we've got to have quantum mechanics. But perhaps we should look at quantum in a different way. We've always assumed that if we say we've got quantum gravity, we're talking about a local interaction. But quantum isn't just local, it's also non-local. It demands non-locality, and at the moment we've got no mechanism by which we can have non-local correlations. So we've only got half of the quantum picture. We've got the local part, but we haven't got the non-local part. Gravity has got lots of differences from the recognised local forces. Its source is completely continuous. There's always energy, mass energy at some point. At every point in space there's mass energy of some kind. All the other sources come from discrete localized points. So that if we go back to our fundamental symmetries, that's what we say. This one has got continuity that the others don't have. So perhaps it's even more unlike discrete sources than we previously imagined. And I tend to think that the Higgs field might be telling us that the amount of mass energy is actually the same at every point in space. And perhaps that never changes. I'm not sure about that, but it's an intriguing possibility that it could never change, that we don't ever transfer energy from one place to another. We simply change its manifestation. That's certainly a point to think about as a possibility. We've looked at our fundamental symmetries. Let's look at our other thing that's important to us, the nilpotent structure. And let's look at what total vacuum might mean, -1 times the nilpotent structure, partitioned by the Kij operators into electric, strong and weak, or in that order, weak, strong and electric. We got negative energy for vacuum, negative energy continuous gravitational vacuum perhaps. So maybe if we have what we call gravity gauge theory correspondent, this is telling us the non-local side of the picture, and the gauge theory is telling us the local side of the picture. Maybe that's what we should be looking at. So maybe it's the continuous gravitational vacuum which supplies the mechanism for the instantaneous transmission of quantum correlations. Now, if we think of it this way, the gravity will have a special nature as a sum of all the other vacuum. And I say this is also hinted at by the 3+1 nature of charge and mass. Very similar to the 3+1 of space and time. Here we've got support from string theory, because string theory also has gravity gauge theory correspondence. Gravity is effectively the sum of the others. Here it's like the sum and cancellation of the others. So if we go on this, we say gravity and gauge theory, which gauge theory is strong and electro weak, they're dual. And I think that's evident in the way that the holographic principle, the one that says everything's on the bounding area, privileges gravity, seems to privilege gravity to obtain information about the entire system. So if we find out what the gravity is doing, we got the information about the entire system. One can be used to provide information about the other. So maybe the fundamental duality is the non-local gravity and local gauge theory. And maybe that's telling us why gravity is so weak. It's weak because to get something equivalent to a gauge theory at a point particle, we have to sum over the entire universe to get the same amount of effect. And maybe it's also telling us why the cosmological constant is at the opposite end to that we would get from quantum gravity. It's on the universal scale, not on the gravitation, on the local scale. Also, in our language, duality always refers to negation. It's so we can get this zero sum, that's why we do it. So if we got gravity acting as dual to the combined gauge theories, then we've got our zero sum. Let's imagine that our combined vacuum is the negative of that nilpotent minus brackets IK, E, etc. Compared to the positive side, we will get by adding the three partitioned bits, the bit beginning with K and the bit beginning with I and J. So let's propose that if we don't apply it to a single local quantum state, gravity is manifesting the whole vacuum, the sole source of non-local correlation, and always applies to the universe at once. And maybe it's giving us the most directly observable aspect of non-locality we can have. This is the logic of if following the symmetry argument. If we follow the symmetry argument, this is what we ought to do. And I say that this has always stood us in good stead, so let's stick with it. Let's follow our logic without exception. We can't complete quantum mechanics unless something is transmitted, communicated instantaneously. And if it isn't any of the local interactions, which we know it isn't, if it isn't gravity, then what is it? It must be outside of physics. There's nothing else. That's all we have. Now, of course, it doesn't mean we don't see a local side of this. We do. We saw before that we saw non-local sides of the local interactions. Electric, strong and weak. There are non-local aspects to those, which are just the other side of the coin. So there must be a local manifestation associated with gravity. And this must be a positive energy thing. Let's suppose that it's what we call the inertial local reaction. Let's suppose that the inertial side of gravity is the local manifestation. And this is what we really observe. We never actually observe gravity. What we really observe is the local inertial reaction. And we say, therefore that means we've got gravity, but it doesn't actually mean we've observed gravity, we don't. We only ever observe a local reaction. So let's represent that by the positive nilpotent structure itself. But this force is fictitious and repulsive. Now if it's repulsive, we haven't got a problem with quantizing. We can quantize the local thing if it's repulsive, because if it's repulsive it must be spin 1. The problem we had with quantum gravity is that it's spin 2, because it's attractive. So it must be it would be spin 1. So we don't have the renormalization problem. Let's say that the continuity of mass energy, the fill vacuum, Higgs field, instantaneous correlation between Dirac states. The fact that energy does not actually move, if that's true, we don't know that it's true, but it's a possible thing that may be true. Let's say those require an instantaneous gravitational force, undetectable direct observation, and only ever observed through the local inertial reaction, which will be dependent on C. and will require a mediator of spin 1. Of course, we know that the gravity will affect that C, because it would for any local interaction. Maybe we've got a non-local due to the combined interactions, which has inertia as its local manifestation. What we're saying here is when we do weak, strong and electric interactions, we do perturbation theory, we do what we call it, a iterative method for finding it from the local state. With gravity, really we have to do the calculation universal. And so I'm saying really it's a carrier of them, but it's also their inverse. It's the opposite. It's not their summation, it's the opposite to their summation. And of course gravity has negative energy because it's attractive, whereas all these others have positive energy. Two identical particles in any other gauge interaction have a positive energy because they repel. The attractive nature of gravity would then be a result of the fact that it's vacuum. That's the only negative energy we have is in vacuum, according to what we've said about the nilpotent. And so in this way we could actually complete quantum mechanics. It's not non-quantum, it's very much quantum, but it's not what we call quantum gravity. If we have this, then we can have a quantum theory, because we've got a method of doing the correlation in quantum theory. If we have so-called quantum gravity, then we've got nothing will give us that correlation, because we haven't got anything, no vacuum. Quantum gravity has no vacuum, so it can't really work. There's some interesting consequences from this. The holographic principle, the one that says which is not yet proved, but it's a widely believed conjecture, states that all the information in the system is contained in the bounding area. And we have that effectively because we have an area created by the E and P terms, which is the same as the K, and the I terms, which is the same as real area by duality, because we've seen that the two spaces are dual. So it's an area in vacuum space, but it's dual to an area in real space. Okay, and we could just simply reverse the roles of the vectors and quaternions in the nilpotent structure. And so that would then determine the nature of the system. Now another concept that's sometimes mentioned is quantum holography. This picked up something of a bad reputation, which is not really valid because it can be demonstrated in a rigorous way, and it has been, for example, by the authors mentioned there. It's probably much less generally applicable, but it certainly works. So you've got a version of holography in which you have your phase and reference phase, or in the same way, but in this quantum holography it's just not degenerate. That's the difference between quantum and ordinary holography. But you could treat your nilpotent as a quantum hologram as much as anything else. And I think my colleague, my medical colleague, I think you've read the paper, Steve, the medical colleague Walter Schempp uses quantum holography, and in his analysis of medical imaging. So now, what are we going to do with general relativity? How do we look at general relativity in this way? The gravitational force is governed by a Lorentzian metric with maximum velocity at the speed of light. Now, we've got to remember, as I said before, that general relativity is not a God's eye view, it's an observer's eye view. We can have a God's eye view and an observer's eye view at the same time. We don't have to have one or the other. As long as we correlate them in the right way, then we can do it. All our observation is local. We've still got to write down how we observe anything. And I think in resolving that connection between the God's eye view and the observer's eye view, we can reconcile quantum mechanics and general relativity. And the only way we can. Let's look at the anomalous precession of Mercury. Now we know that the calculation was done by Leverrier and others, showed that Mercury should precess at 531 seconds of arc per century because of perturbations by the other planets, etc. The measured rate 474, leaving 43 seconds of arc. Now if you look at Newtonian calculation of perturbation theory in the Principia, I found that very interesting when I looked at it, because it wasn't at all what I might have expected. You might have thought it was a calculation doing forces, but it's not at all. It's a geometric calculation. And of course, the Principia is largely a geometrically sorted uses a kind of geometry. It's a kind of calculus type geometry. And what Newton had was that a perturbing influence on an elliptical orbit, he calculated it in such a way that he retained the ellipse. So he devised a system of coordinates which would retain the ellipse under the perturbing orbit, the perturbation of an extra third body in the system. So it would still describe an ellipse, it would still obey conservation of the angular momentum, Kepler's second law, but it would be done in a system of coordinates that varied with time. It would be in a varying system of coordinates. Now, what Einstein does is very similar, but he does it from a straight line. So Einstein has, from a straight line in four-dimensional space, he has that is preserved, the geodesic. The straight line is preserved by using a new set of coordinates, which then become the general relativistic field equations, the space-time curvature. So Newton actually calculated some of the planetary orbits and got 240 seconds for, I think, Saturn and Jupiter. So, but he then said there's no point in going any further. And it wouldn't have made any point to him because he was showing that in his day, any observation wouldn't have got anywhere near that, not even that 240 seconds of arc, so there was no point in calculating it. You had to do the calculations that were observable at the time. Now, he certainly knew that the speed of light was not infinite, but he didn't bring that into his calculation because there was no point. I think this is what I've mentioned already. So the principles are not hugely different. And this was realised by Cartan in the 1920s, who was able to rewrite Newtonian gravity in the Einsteinian structure using tensors and energy momentum tensor and so forth. If you look at that, you can't tell whether there's really an effect or whether it's just the mathematical structure. Is it really space-time curvature? Is it really force? Well, there's no difference in principle. They're both the same. They both give the same physical effect. You can't actually tell. So when people said, no, let's get rid of force, let's bring in space-time curvature, they were just saying, let's get rid of one technique of calculation and put in another. That's fine, no problem with that. But they then said that means something physical. That's what it really is. That's fine. No objection to that. But then you've got to say, what does that space-time actually mean? Does it mean this is what God, as it were, devised, or does it mean this is what we see when we do the observation? So if we assume gravity is instantaneous and non-local, but physical observation is local, involving time-delayed luminal or subluminal interaction, well, we can't use the Lorentzian space-time of a local coordinate system for God's view of gravity. We can use it for ours, but not for God's. So what happens if we say, let's try to express this instantaneous interaction? What happens is that we will create a non-inertial frame for the gravitational system with fictitious inertial forces and a rotation of the coordinate system. That's exactly what happens when we do this kind of thing. Standard Newtonian theory already does this because we know that there's no such thing as an inertial frame in nature. Newton's laws are only true for an inertial frame. So what we do, we avoid the problem by assuming the frame is inertial and then just add on the fictitious forces to cancel the problem that we've done that way, the centrifugal and Coriolis forces. If we had a gravitational system which really was instantaneous, then we would get dynamic equations, exactly the same form, to predict relativistic effect. They would look exactly the same as the Einstein equations. So I'm saying we've got a mathematical theory, Einstein's general theory of relativity. We haven't got any fixed version that we must use to explain it. We're free to choose our explanation that fits physics as we know it. So I think we've already talked about that. In effect, it's the gravitational deflection of light which makes all the difference. This shows how it would happen. That would be a geodesic, a straight line. That's a way of writing down the first equation is a way of writing down the straight line for a light ray, or just a straight line. The second equation is putting dynamic potential. This is purely Newtonian. If you introduce relativity, however you introduce it, whether it's the observer introduces it, or whether it's God that introduces it, then you get something like the first equation. You get the extra 2gm over rc squared. The second equation then would also have the same term. So in effect, this is what we are doing. So what we're doing is saying our physical interpretation has to reflect our assumption that the gravitational force is actually instantaneous, but all our observations are not. So the effect is if the gravitational potential has rotated the local coordinate system. And this constitutes an inertial force term. It's certainly possible to look at this as curvature of space and time, but I'm saying it's not saying we introduce curvature and then that explains the gravitational field, because it doesn't anyway. It is simply a way of describing the gravitational field. So what we're doing with this curvature is describing what the gravitational does to our space-time of observation. That's what we are doing. If we had an absolute system of coordinates, which is impossible, then it wouldn't look like that. We wouldn't have those extra terms, but we don't have such a system. Neither general relativity nor Newtonian theory has constituted an explanation of gravity. It's purely a theory which says space-time is curved, which we say is fine, and that curvature constitutes what we call gravity. But we don't have to accept what everybody else has, not everybody else, but many people have said it means. And I don't think it does mean what they say it means, because if they say what it means, then we will get that not only does gravity cause curvature, but that curvature causes gravity. And that gravity causing curvature causes curvature, which causes gravity, which causes curvature, which causes gravity to infinitum. And this is where I differ from what they say. So we're perfectly entitled to use any physical description which corresponds to the equations. Einstein's general theory of relativity, the field equations, are equations. They don't actually tell you how you must interpret them. They say they're to do with gravity, but they don't say exactly how you interpret them. And so if we say that there is the effects of gravity relating to observation in particular, then we've got a neatly packaged and codified system for doing exactly that. We can solve our problem of the mismatch between the observer and God. So we've got epistemology or measurement rather than ontology, and after all, this is Einstein's position. His is an observer-centered theory. The key thing, there's two key aspects to this. What will be different if we do this? First of all, I think no one has ever proved that gravity travels at the speed of light. Nor do we have to assume that. We have to assume that the speed of light comes into our measurement, without a doubt. All of those things could have been derived from special relativity. Light is special relativistic. If we're using a Lorentzian frame of reference to measure, then we will get the same special effects that we would have if we had light. And in fact, we could even do some of the effects in relatively simple ways. If we look at the deflection of light in the 18th century and the early 19th century, people were doing things like the following equation up there, which is a hyperbolic equation. E is the eccentricity of the hyperbola, light going very close to the sun. One can interpret that as being the sort of time dilation bit of special relativity, and you add on the length contraction bit and you get double the value. However, there's another way of looking at it. Because light is a peculiar thing, because of special relativity, it's a peculiar thing that its velocity has nothing to do with velocity in the ordinary sense. And so when it's drawn into a planetary orbit, it didn't start off in that planetary orbit. And so we could, in fact, use a kinetic energy equation instead, and when we would get the correct value. And there was a calculation published by Solar in 1801 which didn't quite do this. He got that equation, but he didn't do the double integration which you have to do for two angles. And a lot of people said that his value was only half the value. Well, it could have been the full value if he'd done the double integration. Well, that's just a matter of interest. It doesn't make any difference to the way we're doing it. Those are only some of the effects. There are a lot more complicated effects which we have to do in other ways. However, the important thing is that the theory is now linearized. The general theory of relativity is now a linearized theory. It doesn't have a non-linear effects. In other words, it doesn't have the curvature causes gravity, causes curvature, causes gravity to infinitum. That's not true anymore. It's not an additional source. Curvature isn't an additional source of the gravitational field. This time, we say we won't have all these strange things that we normally think we have. Wormholes, infinite gravitational collapse, violation of conservation of energy, unrenormalizable infinities, and quantum gravity. We won't have any of that. We will simply have a linear theory which looks exactly like Einstein's field equations, which is exactly Einstein's field equations interpreted in this way. I say none of those effects have actually been directly observed by any measurement. So every effect which general relativity has observed, and every effect that which it's likely to observe within a reasonable time, including gravitational waves, which also involve an inertial component here, but it's the same principle. Everything like that will happen. It will be exactly as the field equations predict. But all those interpretations which add extra positive feedback won't exist. And the theory will cover gravity and inertia. Now, this morning, I found out this information this morning. I've had to add this slide because it's on a new piece of work. This is a neutron star, J0348. It's got a mass of 2 solar masses, which is higher than people who believed in the non-linearity said could happen, which was 1.5. And it's the second such star discovered. However, that's not what I'm interested in. It's got a white dwarf companion, and it's got a short orbital period of 2.46 hours. So there is no such system been discovered up till now that can do that. And so this is a very, very powerful way of testing Einstein's equations. And what people were saying is that it produces gravitational waves exactly as the equations predict. They expected the equations to break down. They expected extra ripples because this was strong enough, it was short enough period to observe distinct predictions of that. No such thing. They say Einstein's theory is confirmed and we're shocked because it shouldn't have been. At that point, the theory should have broken down because of non-linearity. No non-linearity.
How were those measured? Over the slowdown rate? Or?
I haven't actually looked at any technical details, but it was the Max Planck Institute in radio astronomy. I haven't had time to look at it this morning. I've only heard about it this morning. But this exactly in line with what I was saying. The equations are too perfect, they're saying, but no, they're not. They're exactly correct because this non-linearity interpretation is wrong. So I'm going to follow that with a lot of interest. So I say the relativistic effects really are what I could call an aberration of space or space-time. We're going to incorporate this aberration, and this becomes equivalent to using the general relativistic field equations. That's another way, but I'm looking at it from a physical point of view now. This is my physical interpretation of those equations. And if you simplify it, you've got inertial force corrections of that kind. And these are effectively the same as the gravitational effect and energy transmitted at the velocity of light. And I'm saying we will, by definition, get exactly the equations that we would expect as long as we don't have non-linearity. Exactly, we will get the general relativistic field equations. The full theory of general relativity, though a different interpretation from the one that has been very current up till now. And quantum aspects could be accommodated on the basis of local inertial repulsion spin-1 transmission and create a renormalizable theory. One of the standard ways of doing the effects due to the presence of C in general relativistic equations is to do, say, it's like magnetism and electricity, so you can have gravito-magnetic effect. That's a standard way of doing it. It's standard, but it's not as widely known as it should be, but it's reasonably standard. you can actually, it's much easier to do many of the linear effects just using special relativity. And in fact, one can do that. I'm just going to do a quick calculation on that. Now, a man called Kolbensvet has actually done quite an interesting, a lot of people have done them, but I liked his presentation better than most. He used time dilation as a special relativistic effect. Where I disagreed with him was that he didn't also use length contraction. There must be also the length contraction, so why just stop at time dilation? So I get double the effect he did because I also have length contraction. But otherwise it's very much as he did it. And this is how the calculation. We've got rest frame, mass m, Lagrangian, a particle, and then you get the line element of the rest frame, and then you've got the gamma. So integrate for the rest frame, transform to the laboratory frame, neglect higher order terms, then you can obtain another Lagrangian, the one down below. Then you can compare that with a typical electromagnetic one, and it looks pretty much the same, except there's a factor 4 in it, which comes from the length contraction and the time dilation, because the C is affected by that. The velocity of light is affected because gravity is affecting it. So that's why you get the 4. So it looks pretty much the same. Then you can extend the argument. So that's as far as Kolbensvet goes. And then we can extend the argument, create a gravitomagnetic field. Many people do this kind of calculation. This is my own version of it. And you get a rotation term instead of the magnetic term. So if we're concerned with repulsive forces here, so these are gravitational at second order, as it were, because they are really inertia caused by gravity, but this is the extra term, this is how it's interpreted. So we get a slight difference in that we get positive instead of negative. Now if you look at that equation, an equation like del dot g equals 4 pi g rho, doesn't have any velocity in it, completely insensitive to it. So you can't tell whether you've got velocity of light in that or not. There's no velocity of light in the equation. And we're going to later assume that the static inertial force and the static gravitational force...
It doesn't need to, because
yeah, that's why it doesn't need to. But I say the 4 has been claimed to be an indication of spin 2 boson, but in fact it isn't. It's got nothing to do with spin 2 boson, because you can derive this aspect of the calculations from special relativity, which has nothing to do with the general relativistic side of it. Now previously, as interpreted, general relativity couldn't resolve gravitation and inertia connection. It couldn't accommodate Mach's principle, which is the idea that inertial mass of an object is caused by the interaction with the rest of the universe. And many people have tried to do that, beginning with Einstein, have tried to include Mach's principle, but they couldn't. Now, Sharma, who was Stephen Hawking's PhD supervisor, put forward in 1953, came up with an argument of how one could do this. But he abandoned it, couldn't get it to work. He started off with an acceleration dependent inductive force, which you can derive from Faraday's law of induction. The bottom equation there, the one with Q1, Q2 charges. And then he took a gravitational analog, which you would have got from the Greek gravitomagnetic structure. Then he said, let's suppose that we've got a body of mass m equals m1, and then the action of the total mass within the event horizon of the Hubble radius, which is here called RU, and that mass is what we could call the Hubble mass. And if you did that, you would then make the force equal to kma with k constant. So Sharma required that equation to be true. And if k equals a half, then you get F equals ma. So you get an inertial equation from summing up all the interaction with the rest of the universe. In our interpretation, we have to have a local consequence. The inertia is a local consequence of the universal gravity. So we have to also include the equivalence principle effect. We'll say inertia defines a unit of mass, but so does gravity within the same event horizon. And so we would, by the way, the angular dependence dropped out because of isotropy and uniformity. So we would get that equation. Now, we've gone beyond what Sharma did. We would get that equation by also applying the principle of equivalence and the definition of what an inertial mass means, of a unit of inertial mass. We get an acceleration, and we get that acceleration down below, c squared r over ru squared, which is the Hubble radius. And I first did this about 1979. And if you integrate that, you get the Hubble redshift law. And the argument would be that the Hubble redshift is driven by that inertial. So without assuming any cosmology, we've got an acceleration terms, which in terms of Hubble constant can be referred to as h0 squared r. And if you do, in standard cosmology, the acceleration is also fictitious because it's the expansion of space. It's not an acceleration of objects, an expansion of space. It's an apparent force in standard theory as well as in this one. It would be a completely but all our measurements would show it up as a force. I'm going to not go into detail on that. Now let's combine the inertial repulsive force with the gravitational attractive force, and what do we get? We get an equation like that. And when I did it first, I did it as a Poisson-Laplace equation, but you could also do it using Friedmann equations from general relativity, whichever you want to do, and you would get here vacuum density h0 squared over 4 pi g. What kind of dark energy does that mean? Well, it's very simple to show that it's exact. The cosmological constant would be 2h0 squared, and the vacuum density would be 2/3 of the critical density of the universe. The critical density being the one at which the universe is totally Euclidean, with omega, the parameter, the density parameter equals 1. So I get 2/3. That's the equivalent of that calculation has been standing for a very long time and published in many forms, and I've never deviated from that prediction. Now, when this effect was predicted long before it was discovered, it wasn't discovered until 1998. You can see it obeys Hooke's law, it's proportional to R. That first equation there shows that it's proportional to R h0 squared R. By the way, those two laws, 1 over R squared and 1 over R, are the only two laws which give you a stable orbit. So it would be interesting as explanation, but it isn't explanation, it's prediction. So many years after the prediction was made, an effect of this kind was discovered. And the original data said 74%, which didn't look it wasn't bad, but it didn't look as good as one would hope for. 67% and 74% are sufficiently different for it to be a problem. The latest measurement is 68%. And that came in March after I'd written this lecture, so I had to rewrite this section of the lecture. There's 2 parts of the lecture I've had to rewrite due to experimental evidence. This is what they call the dark energy. Now, I've now written but not yet published a paper in which you can start from general relativity, you can start from the Friedmann equation, you can just work backwards, assuming that it's 2/3. That 68 is really 67. Of course, 67 is within the confidence limits of the value. You could work backwards, and what you would get to is A equals h0 squared r. And if you just take this value as being the key value, you're almost, it's so close to being an acceleration that creates the velocity that you can't explain it away otherwise. You can't then say, oh, well, it's not within. It's like when you got it's not sufficiently within the limits. It is sufficiently within the limit to say that that is physically significant. You've got something that's driving that velocity. That thing is an acceleration. That thing is an inertial acceleration. That inertial acceleration is there to create mass, and that's what vacuum is there for. And so I think we've got something that is really interesting here. So we can justify Mach's principle. Gravitomagnetic effects, redshift and acceleration. If we like, we can generate anything else you want, Schwarzschild metric and so forth, but I'm not going to do those. What we've done here is, using our fundamental reasoning, we've got theories which may have been casted for different purposes, but may not, and we're saying that there's fundamental ideas which can be generated from those results. I knew these long before I knew the theories of Colburn, Svet and Sharma. Once I'd got those theories, I was able to do a more powerful way of doing it, but I had the theory before that. And that was as far as I was intending to go with this lecture. When you read the script, you will find I'm putting into chapter and verse this claim that you can use a spin 1 concept to get a something that might well be renormalizable. But that's quite difficult, and I don't think it's would be appropriate for today. Okay, thank you very much. So, it's good. Sorry.
If I have time for one question.
Yes, indeed, yeah. We're early anyway.
What do you then say about the difference between gravitational and inertial mass? I mean, that must come out in the wash then.
I think they're the same. They work out the same. They are the same. That is the equivalence principle which I've used. They create the same standard.
I'm not sure if you can't say more, because if I understand you correctly, you get the inertial effects automatically, which means rather than our previous position where we have to accept the equivalence principle as an experimental fact, you can actually trace it to to the origin of the inertial effects.
Well, I think you can show by using this mechanism that they are the same. I think this is a proper way of demonstrating that they are. I'm not sure whether that answers your question, but we can think about this.
I think it does, yes.
If I have a book on this, 1994, on some of this. It doesn't have the latest experimental results, but it does have the prediction of the acceleration and so forth. And in my book, Zero to Infinity, I show chapter and verse how that will lead to 2/3. I've got several other papers as well. But I'm hoping to publish a new paper on this, going backwards, so there would be no theory like this in it. It would simply be showing how the experimental data would demand a Machian concept of inertia. Just demand it, which would then drive the expansion, would drive the velocity. The acceleration would drive the velocity.